Have you ever looked at your SAT or maybe Terra Nova scores or some other scores from your past, and you saw that you were, ranked something like in the 63rd percentile, uh, percentile, 63rd percentile, and wondered to yourself, what does that mean? What it means, and we're going to go through here quickly just how to do it, but what it really means is if you looked at everyone, so compared to everyone who took the test, you were above 63% of them. All right? Or another way to say it is 63% of the test takers scored at or below your score. 63% again of all test takers scored at or below your score. This is a graph of the age of U.S. presidents at their inauguration, and it's what's called a cumulative relative frequency, which means, when you get to the last person, the oldest person ever at first age of inauguration looks like 70. So 100% of all presidents, U.S. presidents, were at or below that age at inauguration. All right. Did you know also that in this upcoming election year, this would be the 2016 election year, that if one of the two major party candidates wins, they will become the oldest president during their first term of inauguration. So, interesting point of information there. So, anyways, what does this tell us? Goes along those lines. So, we look at 60, age at inauguration, 60. All right, and then you go across on 60. What that tells us is, looks like 76, 78% based on this graph anyways. 77, let's say 76%. 76% of all U.S. presidents were 60 or below at the age, was their age at inauguration. So 78% of all of our U.S. presidents at inauguration were either 60 years old or younger, because it's a cumulative relative frequency. Cumulative because it's sum total. You can see that the youngest was somewhere like 40. All right. What does that mean? That means 0% of all U.S. presidents were below 40, or one out of however many presidents we've had. When we're doing all of this, really what we're talking about is relative position. So relative to everybody else. That's why we use percentiles. So another way to do relative position or location is called a z-score. A z-score is called our standardized score. So standardized score is what a z-score is. And there's a formula for it, and it's equal to x minus mu divided by lowercase sigma. So what that is you take your score, whatever your score is, subtract the average of the population, and then you divide that sum total. So while there's no parentheses here, there are parentheses there, divided by the standard deviation of the population. And that gives you your standardized score, or your relative score, how you relate to the average. How far away is your score from the average with respect to the standard deviation? Because it's one thing just to say, this is how far away I am from the average, but that doesn't mean anything if you don't know how spread out the data is. Suppose your difference from the mean is 1, but the standard deviation is 10. Well, that means the data is very widespread, so you're only 1 away. That means you're pretty close. All right. What if your difference here was 1 and my standard deviation was 0.2? Well, that means I'm actually 5 standard deviations below the mean, because 0.2 goes into 1 5 times. All right. That's huge distance away from the mean. So it's always relative to, your distance to the mean relative of the standard deviation. So you're wondering how you're going to use this. Suppose you score an 85 on the first test, and the test average is 80 and the standard deviation is 82. If you got an 85 on the next test and its mean and standard deviation are respectively 82 and 8, on which test did you score better compared to all the other test takers. So relatively speaking, which one is a better score? So what we do is we start with the formula z equals x minus mu over sigma for the first test. And then the second test we use the same formula. That's equals over sigma. Plug in values. So z equals 85 minus 80 divided by 10. Over here we have z equals 85 minus 82 over 8. What you're going to do is you're going to find those numbers, just doing the simple arithmetic, find the two z-scores, the red one and the blue one. Now again, they tell you your relative position to the mean. That is, how far you were away from the mean. If you get a positive z-score, that meant you were above average. If you get a negative z-score, that means you're below average. What I want you to do is find those two z-scores, plug them into the reflection response, and then tell me, relative to the other test takers, who did better. So now, what if we take that first test back there, where the average we said was 80 and my standard deviation was 10? What if the teacher decided after the fact that, one of the problems, just everybody got it wrong, so they weren't going to include it. So what they were going to really do is just add 2 points to everybody's score. So we have this hypothetical distribution of test scores. It's a little dot plot here, let's say. Okay, there's my hypothetical dot plot of data. With an average of 80, and my standard deviation is 10. Something like this. So this is 90, this is 100. Obviously you have that one guy who got the 100% over, all right? That one person, And when we do this, if we realize that, we're going to add 2 to everybody's score, what effect does that have on just the data set? So if I took this entire data set, all right, so now an 80 is actually now in 82. A 90 is a 92, 100 is 102. All right. Did this spread of data change if I moved all of them up 2? This graph itself right here didn't grow, it didn't shrink, it just stayed exactly the same. So if every data point has 2 added to it, my new mean, mu sub 2, is equal to 82. My standard deviation of this new distribution is still 10. We'll talk about this in class 2 some, but it's that idea of if I just add something to every single data point, the spread doesn't change because they're still the same spread outness as they were before. The average, however, goes up. So then you say, well, what if we do something different? What if we take every data point, x1, x2, x3, x sub n, take every single data point, and so then my mu of x is equal to mu. So now if I take mu of x plus 2, we just said would be the same as the original mu plus 2. Sigma of x is equal to sigma. Sigma of x plus 2 is equal to just sigma. All right. What if I took every data point and multiplied every data point by 2 and then averaged them? I would have a new mean that's twice as big as the old mean. And if I had a standard deviation, where I then took every data point and multiplied it by 2, it would be equal to 2 times the standard deviation because it's totally being spread out. Now the same thing would be true. What if I did, instead of 1 or 2x, I did half x? Well, then it would be a half of the mean and be half of the standard deviation. Would the shape change? No, the shape would not change, but the center and the spread would definitely change. If there was an outlier before, there would still be an outlier, but the distribution itself would just maybe look a little bit differently. All right, now last thing is, and I've kind of been drawing little graphs and stuff like this, so let's make a left skewed distribution. All right, and we're going to relate this back to percentiles. If we have every single data point underneath this graph, then the entire area shaded would be 100%. Or 1, because 100% is 1 as a fraction, or as a decimal. All right, so then I have another distribution here, also left skewed a little bit. Now I can maybe take just this portion and find that. Let's find out, oh, that's like looks like 0.3. All right, that is 30% of the area is in that range. All right, what I have going on here, these are what are called density curves, where basically this curve is showing all the possible outcomes for some event. And so when I take a portion of it, I find that the area of this portion of it is a fraction of the whole thing, or as a decimal, or as a percent of the whole. So a density curve is always on or above the horizontal line. The area underneath is always exactly 1. And in the curve itself describes the overall pattern of the distribution. Here's left skewed. All right, the area under the curve and above an interval, so from here to here, is a proportion of all those observations, 30% of all the total observations. So if we actually had data to go with this, you could see how that works. But that's the basic idea of a density curve, and that's where we said, like, in this case, it's left skewed, so that means the mean. So if that's the median, right there, the median means 50% is above, 50% of the total area is below that value right there. All right, and then my mean would be slightly less. Let's make it red. Slightly less because the left skewedness skews the mean down from the median. Well, I told you what to put in the reflection response earlier in the video. If you forgot that, you need to go back and figure it out. But it's the z-scores, putting in the 2 corresponding z-scores and telling me which was better overall compared to each of the tests within which they take it. That's it. We'll see you in class.